Hi, I'm Mark Weitzman. Welcome back to our deep dive on the transformation of a W boson. This is part 2. Just to review what we did in the last part where we set up the problem, we have an observer's reference frame, O, and in this reference frame we have a W particle moving in the Y direction with momentum Py. So it has Py, and it has a sigma z component, which we'll call sigma. And we have another observer, O prime, which is moving with a velocity Vz in the direction, z direction, in the reference frame where O is at rest. And our problem is to determine how the W boson state looks in O prime's reference frame. Now, sometimes in relativity these things can get confusing, so let's just set it up carefully. We'll define R as the rest frame of the particle, W boson rest frame. So these are frames. We'll define the frame O, as we've defined it in our diagram, as the observer frame. Observer O is at rest by definition. W has momentum exclusively in the Y direction, Py, and O prime, the observer O prime, has velocity Vz. O prime, his reference frame, is observer O prime is at rest by definition. Observer O has velocity in the opposite direction, minus Vz. And the W boson has momentum which I'll write down in a second. I want to define our notations first. For Lorentz transformations lambda, there are two types of transformations. You can have boost, B, which are just velocity transformations. And we can have rotations, pure rotations. Rotations leave the time component of the 4 vector unchanged. And every Lorentz transformation lambda, this is a theorem, I won't prove it for you right now, but every Lorentz transformation can be written as the product of a boost with a certain parameter and the product of a rotation with a certain parameter. We'll use this shortly. Now, the key thing here in part 1, we proved, or we stated, or we defined, however you want to look at it, we defined that if we boost the particle from rest to, let's say, momentum P, its spin component are unchanged. So you might think that in this particular problem that would solve our problem very quickly, because all that's happening here is we're in the final reference frame, in O prime's reference frame, we know that the W boson is going to have it's just a simple velocity addition that we do in special relativity. It's got a certain velocity in this direction and then a certain velocity in this direction. So we know it's traveling in O prime's frame I'll use primes for O prime, Y prime, Z prime. the W particle is moving something like this. This is its momentum. And you might think, well, okay, so it's moving in this direction. We simply have to boost in this direction, and its spin is unchanged. But this would be incorrect. And for those of you who have studied the Thomas effect, I'm not probably spelling his name wrong here, T-H. Thomas effect in special relativity, actually it's in atomic physics, where the spin-orbit coupling is reduced by half. And this factor comes from special relativity. Because it turns out, as if you've studied this, you know that a boost in one direction followed by a boost in another direction is not just a boost in the resultant velocity, there's also an additional rotation. This is just a kinematic effect of special relativity. So let's set this up. I'm going to use X as general coordinates, and I'm not going to use indices on it right now. I just want to show you how it works out. So basically, the X coordinates in the O reference frame is equal to a boost times the X coordinates in the particle's reference frame. We go from the particles, the coordinates in the reference frame where the particle is at rest, and we boost it. We boost it by the velocity. And the velocity will end up being, remember your special relativity, Py over m gamma. Gamma is the square root of 1 minus v squared. 1 over the square root of 1 minus v squared. So it's like the energy of the particle. M gamma is the energy. So momentum over energy is velocity. So this is how we relate coordinates in the particle reference frame, the W boson reference frame, to the observer O reference frame. And in a similar way, we can relate coordinates in the observer's reference frame to the observers in the primed reference frame. Here the parameter is just Vz times x O prime. X is not just x, it's not this x, it's t, x, y, and z. I'll write down x is like x, comma y, comma z, comma t. Okay. And then additionally, so we can invert this equation. So this implies very simply that x in the O prime reference frame is the opposite transformation, B inverse Vz times x in the observer's reference frame. That's equal to just B of minus Vz. When we invert boost, we just reverse the velocity times xo. Okay. So now we can substitute xo from here and we can get the relationship that we want, essentially the final coordinate transformation. Xo prime is B minus Vz times B Py over m gamma times xr. And this is where the Thomas effect comes in, because we have two boosts in different directions. One's in the y direction, one's in the z direction. And we know that in general, we can write, since we know it's still a Lorentz transformation, we can write this as lambda times xr. So we know that lambda is equal to B minus Vz times B Py over m gamma. But we also know we have this factorization. Once we know the velocity, if we want to know the velocity, I left out here in the O prime reference frame, it's simply the boost to get to the O prime reference frame, the velocity is just given by the boost minus Vz times the P times P. Let's call it Py, representing all four components of Py. So we know that this is also equal to B this is the momentum there, B minus Vz Py divided by m gamma prime. We'll have to calculate gamma prime. It's actually a very easy calculation, times r theta. So now we get the equation that we're looking for. R of theta, the rotation, is equal to B inverse, which will just be a minus sign here anyway, B minus Vz Py m gamma prime times B minus Vz times B Py over m gamma. So I'm just multiplying by the inverse of this to get r theta. So this is our crucial equation, which we're going to have to calculate. It's going to be a long calculation. These always are. And the basic idea here is that the spin doesn't change due to the boost. The boost doesn't change the spin, but there's a rotation. And under a rotation, the components of the W boson spin will change. So we have to calculate this rotation, and then we have to figure out, apply that to the change in the spin components so we can get the final description of the W boson. And we'll continue this in subsequent parts where we'll actually write down each of these matrices, multiply them, calculate the angle theta, and then proceed from there. So I'll see you in the next part. Thank you.